Okay. Okay, next topic is about simultaneous differentiation. We have learned about ODE differentiation. So if you ODE differentiation, we have learned about integration differentiation, differential equations differentiation. So the techniques, I think I already covered, and how the techniques will be conducted. Okay, this is already covered, I think, last week. Okay. So we go for the next topic is simultaneous differentiation equations. So in engineering, we frequently encounter systems whose characteristics are modeled by a set of simultaneous linear differential equations with constant coefficients. So the method solution is essential in order for you to solve single differential equation is in one unknown. So by using Laplace, okay, the system simultaneous differentiation is transformed into system of simultaneous algebraic equation, which are then solved for the transform variable, inverse transform, and desired for the solutions. Okay, for example, here is example 5.2. So solve for t is bigger or equal to 0, the simultaneous first order differentiation. So in this topic, simultaneous differentiation, you will have mostly two equations. So for example, equation number 1, which is dx over dt plus dy over dt plus 5x plus 3y equal to exponent negative t. And you have another equation, which is 2 dx over dt plus dy over dt plus x plus y equal to 3. Where is your condition? X equal to 2 and y equal to 1 at t equal to 0. So means x naught is equal to 2 and also y naught is equal to 1. So this is your initial condition. Okay. Okay. So in order to solve this one, you need to solve the mathematical of the equations. So you need to transfer each of these equations into a Laplace transform. So first we know the x over dt is a differentiation. So we use this type of formula, which is your first differentiation. It's not a second differentiation. So it's xs minus x naught plus the second is for ys. Okay, this is x. The x dt formula. Okay, this is under the x dt. Okay, mine plus this is under dy dt. So 5x become 5xx and 3y become 3 bigger ys and equal to exponent 1 over 3. We know that based on exponent 1 over 3, we get this 1 over s plus 1. So then, for the second equation, we change it to the Laplace transform. So this is 2, this is 4, dx dy, dx dt. Okay, this is Laplace. So this is for dy dt. And this one is x and y and 3s. Okay. So first, we need to transform into Laplace transform. So you have a two equation in Laplace transform. So next is we put it the condition first because we want to eliminate some of the Laplace formula. For example, x naught equal to 2 and y naught equal to 1. So in this case, it become x naught become to 2. This one will be 2. Okay, this one will be 1. So when you calculate this one, what you will get, okay, and you put it your x and y in the left side and the rest in the right side. Okay, so what you will get, s plus 5xs plus s plus 3ys is equal to 3 plus 1 over s plus 1. So we make it in the proper way is 3s plus 4 divided by s plus 1. Okay. So the second equation, which is 5.2, so we simplify it by changing the x naught and also y naught. So you will get this one, the similar one, and the right side is 5s plus 3 divided by s. So now you have equation number 3 and also equation number 4. So the pair of simultaneous differential equation of equation number 1, equation number 2, which is in xt, has been transformed to equation number 3 and number 4 in terms of variable xs and ys. So we remain xs and ys here. Okay, so this one will be solve it simultaneously. Okay, to now be solved simultaneously xy. So what you need to do, you eliminate, for example, the first you eliminate ys. Okay, eliminate ys. So you will get the formula of xs. Okay. So when you eliminate, you need to make sure how to eliminate. You need to times. I think this is straightforward. Okay. So make sure that eliminate ys, then you will get xs. Okay. The moment you add xs in Laplace transform, you need to use your partial fraction. Okay, partial fraction to get the correct Laplace of the partial fractions. Okay, then you change the partial fraction from the Laplace transform in terms of frequency s to a y xt. Okay, we know that the first one is negative 9/2s is become 9/2, negative 9/2. Okay, the second one is 11/6s plus 2. So is equal to negative 11/6, the constants and exponent negative 2t. Plus the third one, 25/3 s minus 1 become 25/3 exponent 3. Okay, so which is your t is bigger than 0. Okay, so done. Solve the x s and xt. So next, what you need to do, you need to change by eliminating xs. Okay, eliminate xs, then you will, in order for you to get ys. So you get the formula of ys. Okay, so the moment you get this one, as usual, you need to use the partial fraction. Okay, so you will get these constants. The first is 5/2s plus 1/2s plus 1 plus 11/2s plus 2 minus 25/2s minus 1. So this one you need to, which is inversion give. So you need to change from the ys to yt. Okay, so you just transform again into yt. So this one will become 15/2 plus s plus 1 become 1/2 exponent negative t. Then this 11/2 plus exponent 2t. Then the minus 25/2 exponent t. So you will get a formula of yt here. So with these two equations, okay, the solution of given pair simultaneous differential is this one. So this is your final equation of x. Okay, then this is your final equation of t. Okay. Okay, note, when solving pair of first order simultaneous differential equations such as equation 1 and 2, an alternative approach obtained in value yt having obtained xt is used in 2 and 1. Okay, so what you need, that's the first solution. What is another one is you can start to eliminate first the dy/dt based on the original equation. So eliminate the dx/dt. Okay, so you eliminate that, you will get 2y dx, sorry, eliminate dy/dt. So not dx/dt, dy/dt. Okay, eliminate dy/dt. So you have dx/dt and the rest. Okay, so what you need to do, you can simplify it. So it remains dx/dt. So 2y on the left side and the rest will be on the right side. Okay, then substitute solution obtained in 5.25 for xt. Okay, we get 5.25 just now. Okay, xt. Okay, so you substitute this xt inside of the equation. Okay, dx/dt. Okay, dx/dt, you need to differentiate your xt. Your xt here is x. Xt is negative 9/2 minus 11/6 exponent 2t plus 25/3 exponent t. So you substitute this one inside of here. So this one, the first one is dx/dt. So you need to differentiate this one into dx over dt. Then, okay, the answer of this differentiation, okay, so differentiation of dx over dt, you will get 11 over 3, okay, this one will be 0, this one 11 over t, okay, exponent negative 2t, okay, plus 25 over 3 exponent t. So this one you need to put in this dx over dt, okay. Then this is x, so you just put this x inside of this one, okay. So you will get the equation. Then you simplify the equation, automatically you will lead your answer into the y result. So this is another way. So instead of your calculating xy using the Laplace transform, another way is you just solve the xt only, dx over dt. So you use the first equation of the main equation. So you just substitute it, then you will get the y. Okay, you get the similar y. This one 15 over 2 plus 1 over 2. So you get the same one. So they have two methods here. Two methods. So which one is you solve it? The first method will be solve from Laplace. You need to find xs, okay, xt, ys. Then you need to buat simultaneous. Okay, you get the xt and yt. Second method will be based on the Laplace. What you need to find only as x to xd. Okay, then you put this xt inside of the equation, the first equation of yt. Then you get the same answer. Okay, this is simultaneous differential equation. Okay, next is about the Heaviside step function. So in the previous section, 5.253, we consider linear differential equation in which forcing function were continuous. So in many engineering applications, the forcing function may frequently be discontinuous. For example, a square wave resulting from on and off switch. Okay. In order to accommodate such a discontinuous function, we use the Heaviside unit step function (HT), okay, which as we saw in section previously. So if we explain to you Heaviside step function, I think you have learned it previously. So HT have a limit of 0 to 1, where is your t below than 1 and also t above than 1. So Heaviside step function frequently referred to simplify as the unit step function. Okay. So for example, a function represent a unit at t equal to a may be obtained by horizontal translation of duration a as depicted in this picture. Okay, for example, ht minus a from 0, t lower than a and t higher or than a. So what happened, for example, the a1, okay, 5.1a shows the normal of t minus a, which is 0. So you will started from below than t is below than 0 with 0. Okay, this one is a h t equal to 0, 1, whereas t is below than 0 and t is bigger than 1. Okay, bigger than 0. Okay. So your step function will be something like this. But what happens is there is a condition of a, any numbers. Okay. So the step functions of Heaviside step function will be based on the a, for example. So for example, you have ht minus 3. So this, your step function will be 3 here. Okay. So below than 3 will be 0, above than 3 will be 1, for example. This is a Heaviside step function. So in terms of Laplace transform, how it will take the product function of ft, this is your function, which is need to times with the Heaviside step functions, takes value. So your limit will be ft times ht minus a. So your limit will be 0 to the function. The function is ft. So when t is below than a, become 0. When t is bigger than a, become ft function. Okay, where is your h t minus a may be interpreted in device of switching. So it's like the jet logic diode 1010, something like that, lah. Okay, the Heaviside step function will be function. Okay. So in this way, the unit, okay, the application of step function normally Heaviside is like diode, then also will be I just said it just now, logic, jet logic, say, for example. So it's more on control. We will use this mathematics. So in this way, the unit step function may be used to create a concise formula of piecewise continuous functions. So to illustrate this, consider piecewise continuous function ft of figure. Okay, so what happens is the function. So there will be a function of ft1, f1t. So where it started from 0 to below than t1. f2 is from t1 to t2, for example, and f3 is t2 and above. So in terms of Heaviside step function, what happened is, based on the function, each of the function have different function and formula. So to construct this function ft, we could use this formula of switching operating. For example, switch on the function f1 t1 is equal to 0. So this is the first function, for example, linear function. From 0 to t1, this is the function. Okay, for example, a linear function. But what happened for function number 2, f2, switch on the function, the second, the t1 and above to t2, the function are not the same. So something like, for example, is a quadratic and the same line. So t1, f2, t at t equal to t1, and the same time switch off the t1. So the c1 is f3 is another function, for example. So by using Heaviside step functions, you can make it a step function easily. So in terms of unit step function, the function may thus express, just now we have a function. So ft, the first function, you need to times with the first ht. The second ft, which is this, plus f2, function of number 2 minus function of number 1, okay, times with Heaviside step function of t minus t1, plus function number 3 minus function number 2, which is h minus t minus 2. So alternatively, ft may be constructed using top hat function ht minus a minus ht minus b. Okay, so in this case, clearly that ht minus a minus ht minus b is from 1 to 0, whereas your t is a and b, and 0 are for otherwise. So when in transform, Laplace transform, you just multiply with the function. For example, this one is a ft function. Then you times with this Heaviside step function. Then you will get these new conditions. Okay, for example, it's a top hat function here. Okay, using this approach, the function of ft in this figure may be expressed as 5. Okay, from this figure just now. Okay, from this figure, so we can change this to a Heaviside step function, something like this. So what happened is, here we have a 3 function, which is f1, f2, and f3. Okay, we have f1, f2, f3. So based on here, what you need to do is, for the functions of this one, you need to times f1 times ht minus t minus 1. So plus f2 times ht minus 1 minus ht minus 2. So means that for the first, okay, first function times Heaviside the first function minus the second function, okay, plus the second function is a Heaviside previously t minus 1, here t minus 1, this one, minus the next one, t minus 2. Then f3 is times this t minus 2. So this one, if you can simplify, it become f1 t ht, okay, plus f2 t minus f1 t ht minus t1, plus f3 t minus f2 t ht2 minus 2. Okay, so we can easily check that the h1 happen when ht minus 1 equal to ht t minus 2 equal to 0. Then for the ft equal to f1, which is t is between 0 and 1. And while t minus 1 is equal to 1, t equal to 0, whereas your final function will be ft f1 plus f2t plus f1 plus f2t. Yeah. Okay. Finally, this is the functions. Okay, you will get something like this. Okay. Okay, we go for examples. Okay, this will give you a more clearer picture. Okay, expressed in the term of unit step function of piecewise continuous causal functions. So you have three functions here. You have f1, you have f2, and you have f3. Okay, the first function is a quadratic. Okay, for the function of ft, so something like this, you start from 0, 0 until 3, 3. So the function 2t squared, so the graph will be something like this, 2t squared. Okay, the second function will start from 3 until 5. It's a linear function, t plus 4. And the third function is a linear, okay, from 5 to and above. So it will be 9. So we straight line. So you have a 3 function here. In order to change to unit step function, okay, what you need to do is from this graphic in terms of unit step functions, so you need to times each of the function with the ht. Okay, what happened is here is the main, okay, I put it here, ft is your main function. So the first function is 2t1. So 2t squared, sorry, times h of the first function of ht plus, okay, the second function will be t plus 4. So 3 plus 4, but you need to minus the previous function. So will be t plus 4, this function, number 2 function, minus with the previous function, 2t squared. Okay, now your h will be times t minus t3, means that the first t minus the current limit, t3. Okay, so then plus the next is the third function. The third function, so what you need to do, put the function first, 9 is the function, minus the previous function, t plus 4, so become minus 3 minus 4, okay, times the h will be the limits of t from t minus 5. From the t minus the limit of 5 here. So this is your unit function started, okay. So you can simplify this one. This one will remain the same, 2tht. This one you can get this formula, okay. Then so then this is how the simplify, like I said, simplify. Okay, so this is on how the Heaviside function works. Okay, we go for second examples. Okay, second examples, Heaviside functions. Okay, you have a few functions here. You have f1 here, f1t, f2t, f3t, f4t, and also f5t. Okay, you have 5 functions here. So as been previously, okay, in order to change this term into a unit step functions of piecewise continuous causal functions, so what you need to do is you have a ft, the main one ft. Okay, first, what is your first function? Your first functions here is sorry,
0.
0 and 0.
Yes.
0 times h t,
Yeah.
ht, so it becomes 0 actually. Okay, plus the second function 1, okay, this is 1, okay, times with the h of t minus the t1, the limit of the starting point or previous point, 1. Okay, plus the next function will be 3 minus 1, the function 3 minus 1, your 3 minus 1, that's your function. Heaviside step function is t minus 3. Okay, so you will take this one. Okay, then plus the next function is 2 minus 3. This is your function ft. So times h of tn. So h, what is your t? T minus 5. Okay, the previous one will become 5, or this one. Okay, then plus the final one, your function is 0 minus 2 times h t minus 6. Yeah. So from here, you should simplify it. So you will get something like this. Simplify this one. Okay, this is your unit step function. So in terms of graph, we can see here it will start from 0. Okay, from the limit 0 until 1. So when 1 and 1 to 3, okay, 1 to 3 is 1. Okay, we will move on 1. 3 to 5 will be 3. Okay, then 5 to 6 will be 2. This is based on here, function there. Okay, 0 to 1, 0 to 1, below than 1. Then this is the original before step function lah. So 2 to 3, so something like this lah. So this is the step function. So what you need to do, you just times the function with you just use the formula lah, minus the function minus the previous function times the limit of t and the rest lah. Okay. Okay. Another one is a Laplace transform of unit step function. Just now is Heaviside step function. Okay, Laplace transform unit step function, by definition of Laplace transform, from the transform of h t minus a. So a is bigger or equal to 0 is given by this one. Okay, we know that the Laplace of h, it will be integration of 0 to h of the function times exponent negative st. So when we simplify this one, put the limits at the end, the Laplace transform h t minus a is exponent negative as divided by s. Okay. So same like the shift concept, shift theorem. So when you have a Laplace transform of 3 minus a is exponent a, for example, your a is 3, it will become exponent 3s divided by s. So this is the formula that you need to understand. But what happened when a equal to 0? So which has t will be 1 over s. Okay. Okay, this is similar like previously. So we go for the examples. So determine Laplace transform of rectangular pulse. So we know the function, the first function is 0, where is t below than a. The second function is k, which is your t is between a and b. Okay, and the third function is 0 when t bigger than b. Okay, the pulse is depicted graphically in figure 5.2. In terms of unit step function, it may be expressed using the top hat function as ft equal to k ht minus a minus ht minus b. Then taking the Laplace transform, so you have this function. Okay, so the first one is 0. The second one is k ht minus a minus ht minus b. So in order to Laplace this one, Laplace of ft, you need to Laplace 1 of 1, each of the constants. So that's why we k is the constants of the Laplace of t ht minus a minus k is the constants of Laplace ht minus b, something like this. So when you have this one, you need to Laplace 1 by 1 Laplace this one and Laplace this one Okay, so the moment you have Laplace this one, so we know that h minus t, you just put the formula k minus exponent as divided by s minus k exponent bs divided by s. So this one can simplify, become ks, just take out the ks, so you will get exponent negative as minus exponent negative bs. So this is on the Laplace transform of unit step function. Okay, so determine the Laplace transform of piecewise of ft shown in figure 5.2. 0.23 from here. Okay. So this is the function, the main function just now. Okay, this one, okay, from this equation, so you get this one. So determine the Laplace transform. Just now is Heaviside function. We change from the normal equation to Heaviside function. Now is we want to do it Laplace transform of the piecewise. So this is the equation prevalent in terms of function t. So the same equation like example 5.23. So where is your first one is 1 times ht minus 1, 2 ht minus 3, minus 1 ht minus 5, minus 2 ht minus 6. Okay, so what you need to do next, you need to Laplace each of the equations. So we Laplace the first one first, the constant remain outside, then the Laplace of the t minus 1 plus 2, the constants, then Laplace of h minus 3 minus 1, the constants, Laplace of h minus 5, minus 2 constants, which is Laplace of h minus 6. So you need to solve one by one. We know that t minus 1 in Laplace exponent as, your a here is 1. So that's why negative exponent negative s over s, plus the second one is put the constant of 2, Laplace the second function, the h function. So we know h minus 3 is exponent negative 3s, your a is 3. So become 3s divided by s, minus 1 is the constants, then Laplace of this one will be exponent negative 5s divided by s because your a equal to 5. Then the last one minus 2 exponent your a equal to 6, so become negative a num 6s over s. So you will get this Laplace transform of this formula. So you can simplify this one, just take out the 1 over s, then remain the exponent inside of the bracket. So you will get the Laplace transform of Heaviside function, okay, or piecewise constant. Okay. So first thing first, solve the Heaviside. Normally lah, the concept. Okay, Heaviside. Sorry. Step function. Then second Laplace of this one. So this is the concept. Okay. Okay, we move to next is second shift theory. Okay, this theorem is dual to the first shift theorem given by the theorems and sometimes referred to Heaviside and delay theorems. So same concept, but we use this first shift. First shift normally we use this FS, the big FS, GS, something like that lah. Previously we normal linear we do from XT to function lah, XS for example, something like that. So now the main formula of Laplace of FT Fs is equal to Ft minus A times Ht minus A is exponent As times Fs. So this is the main formula that you need to remember how to use it. Okay, if Laplace transform Fs, then positive a constant of A of these functions. So how it prove is, this is how it prove lah. So the Laplace of these functions is equal to Laplace of the first function times exponent negative ft. So then we simplified it. Okay, we change the t to t minus a. We put it here. Then we simplify. At the end of the day, you calculate, you integrate. Okay, you will get ft exponent ft. Then you get this function. This is how exponent negative as Fs works. Okay, so this second shift theory is important to distinguish between two functions. So which is Ft Ht minus a and Ft t minus a Ht minus a. As we saw earlier, Ft Ht minus a simply indicate that the function of Ft is switched at time t equal to a, so that of this function of t minus a, so means a is the main one. If below than a becomes 0, if bigger than a, the diode will be on, for example lah. Okay, so it's a function. There is a function. It's below than this 0 a, so they'll be off. So that's why you can see that. Okay. On the other hand, if the function minus a times the ht minus a representation of ft by unit of the right. So the functions of inside here also, instead of t, become t minus a here. So this one is the difference. For example, the first functions of the first function is the normal functions. Okay, what happened? 0 to me, then it start from a. But when we have t minus a, the function will be 0 until a, then it start to be the function. But if a function minus a times the ht minus a, the function will start 0 from here, then it will be started from 0, from a to above will become 0. So this fa, fta, hta may be interpreted as representing the function ft delay in the time of units. Thus, when considered its Laplace transform exponent fs, where fs denote as a Laplace of ft, the component of exponent may be interpreted in delay operating of the transform ft. Fs indicate that the response of system characterized by the fs. Okay, so since many practical important systems have formed, okay, this is in terms of the delay. In terms of mathematical calculation, how it works, yes, determine the Laplace transform of the ft. So you have a two function, which is your function t, where is from 0 to b. Then second function is 0, where is your function is t to b. So what you need to do, you need to create the function first. So from here, you will create the function ft is t times ht minus t, ht minus b. So in order to apply second shift theorem, each term must rearrange to be in ft minus a, ht minus a. So that is the time argument of t minus a of function must be the same as the associated step function. So you need to make sure everything is t minus a. So the first function will be t ht, okay, this is initial, minus t minus b, okay, ht minus b minus b ht minus b. So in order to Laplace it, you need to Laplace one by one. Laplace is 1, Laplace is 1, and Laplace is 1. Okay. So when you Laplace the first one, you will get 1 over s squared minus exponent, exponent negative bs. Okay. Laplace of t, okay, minus, you open the bracket, Laplace of t minus b exponent negative bs. So you will get the Laplace transform something like this: 1 over s squared minus exponent bs divided s squared minus b exponent bs s. So Laplace of ft is equal to 1 over s squared, 1 minus negative bs minus b over s exponent bs. So this is the giving. So from here, you can, this result could have been obtained without using of a second shift, since directly definition. So this is another way, but if you use a direct definition, integrate as, so you get the same one. So this one using the shift theorem. Okay, we go to second examples. Obtain the Laplace transform of piecewise causals. So you have the three functions as 2t squared, t plus 4, and 9. Okay, so first thing first, you need to change this one in terms of the Heaviside step function. Okay, I think I taught you just now. The first function minus the previous function, ht, minus the t minus this one. I think I explain this one. So once you have this one, we can find the Laplace of ft is the function of 2t must be expressed in function of t minus 3. So you need to change this one in terms of 3 minus 3. Okay, because of this t minus 3. So this may achieve of z equal t minus t. So what happened here, if 2t minus t minus 4 is equal to 2, change the z equal to z plus 3 minus z plus 3 is equal to 4z. So you solve it, you will get the answer of the z. Okay, once you have that thing, you have changed from the normal step function to t minus 3. Okay, then you can Laplace of this each of this equation, because in this shift function you must make sure h t minus a. So you have a main function, you need to change to t minus a. In this case, t minus 3. Okay, you can see t minus 3 here. Mostly 3 minus 3 and 3 minus 5 lah. Okay, so you need to Laplace one of it. The constant remain outside. So Laplace the t function and also ht function. Okay, so when you have Laplace this one, so you will get 2 over s minus exponent negative ts, Laplace of 2t square plus 11t plus 11 minus exponent negative 5s L over t. Then this one will be Laplace something like this, 4 over s power cube minus exponent negative 3s, okay, times the constants of the Laplace 4 over s cube plus 11 over s square plus 11 over s minus exponent negative 5s s square. Okay. Okay. Okay, we go for the last one. Inversion using the second shift. Okay, previously we have learned about the using the second shift. So this is the theory of second shift. So which is a Laplace inverse of exponent negative a as fs is equal to the original of the function of t, which is f t minus a h t minus a. So as we mentioned, if we have a function times t times the ht, if we Laplace it, it become Laplace this one. So it will be Laplace this one, you will get fs. Okay, if you Laplace transform inverse of fs, so you will get the same one, ft ht. Okay, so this is the main one lah. Okay, inverse the fs, second shift theorem, you will get ft times h. So in terms of Laplace, inverse of this function, which is exponent, inverse of exponent as fs, so it's equal to the ft ht, where is t replaced to t minus a. So this indicates that ft has been delayed by unit of unit a. So normally, this in terms of the, you will delay a little bit of a units, for example, 3 seconds or something like that. Okay, for example, we have an equation of Laplace inverse of 4 exponent negative 4s divided by s plus 2. So this can be written in terms of second shift, where is your fs inverse of exponent negative 4s fs. Okay, so your function fs is 4s. Okay, so we just take out, because you know that the previous term of shift theorem is negative exponent negative as fs. So you want to change this negative exponent negative as fs. So in this case, the function can be changed into this one, where is your Laplace inverse of negative exponent negative a. What is your a? In this case, your a is 4. So we have a negative 4s here. So times fs. So you have a two function here, which is your fs is 4s plus 2. Okay. So your function is f 4s plus 2. Okay. Based on here. So first we need to obtain the ft or fs. So we solve one by one. Okay. In this case, you need to use your partial fraction. So in this Laplace, you need to master your partial fraction. So you have the fs equal to 2 over s minus 2 divided by s plus 2. So this one change inversion into the ft, where is your 2s become 2, where is minus 2 over s plus 2 become constant 2, 1 over s plus 2 become negative s negative 2t. So this is your ft functions. Okay. So what we can say here, the Laplace inverse of exponent negative 4s plus 2 is equal to negative Laplace inverse of f exponent negative 4s fs. Okay. So f t minus 4 h t minus 4 is equal to 2 negative 2 exponent negative 2 t minus 4 h t minus 4. From where it comes? Because of, you remember, we need to change to f t minus a h t minus a. So where is your a here is 4 here. Okay, so that's why f t minus a is 4, h t minus a is 4. So this one, if you change to Laplace solution, you will get 2 minus 2 exponent t minus 4 h t minus 4. So in terms of giving of this Laplace inverse. So you will get the limit from t below than 0 is 0, t above than 0 of this function 2, 1 minus 2 exponent negative 2 t minus 4. Okay. So what happened here? The first graph show ft function. But what happened when you have a t minus a delay of a in this case 4. So this same function will be delayed start from 4. So that's why this one function is ft. It will be start 0, 1, 2, 3. But if you have a delay t minus 4, it will delay 4 seconds, for example. So each of the function will be delaying 4 seconds. So that's why the graph is the same, but it started from 4 to above. So this is okay. Okay. So next, if you have these functions, the first function is you need to change this function into the second shift theorem, which is this formula will be Laplace inverse of exponent negative a. What is your exponent a? Is s pi time the function. In this case, your fs will be the remaining, which is s plus 3 divided by s squared plus 1. So this is the same like this. Next is partial fraction. You will get this one. Then you change your inversion, okay, in terms of t, ft. So you will get t, okay, 3s become 3 minus 3s squared plus 1 is a cos t. And this is 1 over s squared plus 1 is become sin. Okay. So then you need to change from this second shift to second shift. So exponent fs, which is exponent t minus pi, okay, and t minus pi. So you have a 3 here, 3 minus t cos t. T is t minus a. So we need to change from t to t minus a. Your a here is, your a here is pi. Okay, so that's why 3 cos t minus pi plus sine t minus pi and ht minus pi. Then we can solve this one. So that's which your limit of this function inverse is 0 when t is below than pi, and 3 plus 3 cos t minus sine t when t is above than pi. Okay. So this is the form of the function. It's a cos function and sine function. So it will started from 3. So we start from 0 from here. So you started from 0, then it will be sinusoidals. But the second function is t minus pi. So it will started from pi here. So there is a delay of pi here. Where is your a is pi? Okay. I think that's it from today.